In this demo, we are now going to run the North Pacific example. So I'm going to go here in the ROMs example and Pacific directory. Sorry, I'm going to change directory. And at this point, we have created in the input directory all the netcdf files that we need to run the model. So the first thing, and we also have created in the previous, using the previous demo, we have created the executable npacific ROMs. So at this point, in order to run the model, we need two things. First, we need a .in file that contains the input parameters such as the time steps and so forth. So I'm going to go in the input directory, and since I don't have any, I'm just going to copy one from one of our previous examples, like the shallow water 2D, and an input directory in shallow 2D.in, and I'm going to call it npacific.in. Okay, so now I'm going to start editing this particular file, npacific.in, and I'm going to go down and first verify the number of processors that I want to use. And for this particular example, I want to use, instead of 4 processors, I want to use 8 processors. So I'm going to change this into 4, so that it's 2 by 4. Now, the number of times is I want to run for about 10 years. But before I do that, I have to adjust some of these parameters. Now, the first thing is this model resolution is about 65 kilometers out of resolution. And in my experience says that approximately time step of 3,600 seconds will do. But we can test how long or how big or how small we can set this time step by looking at the current condition while we start integrating the model. But this is a good start. In general, on a 10-kilometer resolution model, 1,200 second time step is a good start. Now, because we have a three-dimensional model, ndfast can no longer be just equal to 1, but we have to set the number of barotropic time steps to something that is higher than 1. And in this case, a typical good value that I use is about 50. Okay, and I don't have a recipe to tell you about how to choose these, other than look what previous examples have worked. And if you really want to know more, of course, you can read the papers, for example, by Shikepting on the model time stepping, and it will give you some additional criteria. But this is experience is not a bad way to start. So that's the time step, and if I decide to have a time step such as this, then I want to do, in this case, for example, a 10-year run. So I have to compute how many time step I need in order to have a 10-year run. And I can do that by, for example, I can go in MATLAB. First I'm going to go in ROMs, examples. And I'm going to go in npacific. Okay, and I'm going to go to MATLAB. Okay, and then I'm going to run MATLAB. And so I want to say I have 10 years times, say I want a year of 360 days, times 24 hours, times 60 minutes, times 60 seconds, divided by 3,600. And that will give me approximately 86,400 time steps in order to produce a 10-year simulation. So I can go back here, and I can change n times to be equal to exactly that. So that's about 10 years. Okay, so then we can go down. And the next thing is to configure the output of the model, the histories and so forth. In this case, I want to write a history file maybe every, let's start with the average files. The average files, I want to write it every month. I want to write an average. So a month would be equivalent to 30 days. So 30 days is about 720 time steps. So I'm going to go back here, and I'm going to change this into 720. Okay. And then, because this is a long-term run, I'm going to define an average file, say every 12 months, which would be equivalent to number of time step is 720 times 12, which is 8,640 time steps. So I'm going to put that, I'm going to say that every 8,640 time step, I create a new average file. And so that means that every average file will contain 12 records, which are the monthly needs. Now for the history file, what I'm going to do actually, I'm going to write the history every 15 days, which is just half of that. And also for the, 360. And I'm also going to define a history file every year, and so I'm going to put the same value that I put in this case. Okay, so I'm done with this. Then I'm going to go further down. In this model run, I've enabled the diffusivity, in case the Laplacian diffusivity. So I need to define some coefficient. I'm going to use for diffusivity about 20 meters squared per second for temperature and salinity. And I don't have any additional tracers, so only the first two need to be initialized. But if you had a passive tracer, for example, you would need this also to be initialized if you want to use it. I'm also going to use some viscosity, and in this case I'm going to start with something like 40 meters squared per second. Now how to define these coefficients? There is ways to define these coefficients. You know the units. So for example, 40 meters squared per second, you know that if, for example, in the time step of the model, which is 360 seconds, so it's 40 meters squared per second times 360 seconds, this is one time step. And if I now take the square root of that, SQRT, that means that in a model time step, I'm going to mix momentum within a spatial distance of about 379 meters, right? Because this is, I have meters squared per second. If I multiply by the time, I get a meter square. I take the square root, and that gives me the distance in meter in which I mix. So that means that if my resolution is about 86 kilometers, it's going to take a lot of time step for the model to mix things within one grid point. Okay, so that's your choice, and for now, not to put too much viscosity because there's already some implicit viscosity, but that's the way you want to understand how to set up the viscosity and diffusivity, and so you can play if you want to, for example, mix things within one grid point every time step, then you would have to use a coefficient that is it's going to be in this case, let's see, 65 kilometers is the average resolution, times 1,000, and these are meters, okay? So then you square this, right? So now you have meter squares, and that's the meter square, okay? So that's the number, and then you divide this by the time step, which is 3,600. And so if you wanted to mix everything in a grid point within one time step, you would have to use a viscosity that is this strength, and that would not be advisable. But this is the idea. Okay. So having said that, let's go back. So we put some viscosity. The next thing that I want to do is I want to since we're using a vertical mixing coefficient, a vertical mixing scheme, the KPP, we also want to enable some background vertical mixing that happens when the KPP is not active. So this is in the interior. So here, a good value is 1 10 to the minus 6. I'm just going to, put these to 1. And for the vertical, so this would be AKT stands for the background vertical diffusivity for tracers. And this is now for momentum, and here I'm going to use an order of magnitude bigger. So I'm going to put this to 1 10 to the minus 5. Okay, so that's another thing. And the next thing is I'm going to go further down. And here we have our bottom drag. And in our previous examples, we used zero bottom drag. Because we were looking at this in this very analytical simulation. But this is a realistic case. In this case, a zero bottom drag is not advisable, and it's going to screw your simulation. And so because we use quadratic drag, we're going to enable this quadratic coefficient. And this number, I've never really changed it, and it's a bit esoteric, again, how to choose the quadratic drag coefficient. But the model is very sensitive to this. And this is apparently a good parameter. If you were a good scientist, which I probably am not so well, you would do some research in trying to better understand each one of these parameters. But if you don't have time, I guess you start with something. But be advised that there is a strong sensitivity on bottom drag coefficient in this particular parameterization. So this is just being honest. So the next thing that I want to do is I need to put the stretching parameters for my grid, and these I can look in MATLAB, the ones that I set. So I'm going to do RMP grid load and the npacific grid, and then I'm going to type GRD, and if I go further up, I'm going to have somewhere my parameters, which are 5 and 0.4 and t-climb 200. So I'm going to go. Sorry, HC is 30. There's a bit of an imbalance here. This t-climb, no, this is fine actually. So here we're going to set this to 5, and we're going to set this to 0.4. Now this is important that you do that, otherwise your initial condition and boundary condition will all be screwed up in terms of the grid interpolation. Okay, so we've done this so far. So the next thing is all this can more or less be left as is, but we have to define our outputs. Where are we going to store all the files of the model? So our input, for example, now the grid is no longer shallow 2D, but it's called npacific, and so we're going to change that. It's the initial condition. The climatology file, we did create a climatology file, but we don't really need it in this case because we don't have any nudging. But we use this climatology file to extract an initial climatological condition and the boundary conditions, which I am going to put in this case because we have an open boundary, pacific-ERY.NC. Okay. The climatology, therefore, we don't really have to input the name. But if we decide later to do some nudging to the climatology, then it's maybe a good idea to just have it there handy so that in case we want to use it, we have it already configured for us. So, having said that, I think it's actually clear. Okay. Next thing is the forcing file, and here the only forcing file we have is called, and it's an input directory, and it's called npacific-4.nc. Okay. So at this point we're done with the initial condition file. So all we need to do is we need to run the model. And again, you can copy from the previous example. You can copy one of the PBS scripts, like run model PBS into there, and you can change this PBS script. In this case, we want to run with 8 processors, so I'm going to use 2 nodes times 4, which is 8. And then here, all I need to do then is I need to change npacific the various parameters. For example, this is the executable, so npacific.roms, and the .in file, which is npacific.in. Okay, so at this point I have all I need, and so all I need to do then is to submit the job and verify that the model is running. Okay, pstat. And right now it's in the queue, and that's because probably there's a lot of people running. And since I'm going to kill this for now. Well, let's see if it started by chance. Pstat, it didn't. Okay, I'm going to kill it for now, and I'm going to run this interactively just to check whether it's running, and I'll do that in the scripts directory. And here I'm going to copy from a previous application one of the scripts to run the interactive run. Scripts run. Okay, I think I have it. I have specific. Oops. I'm going to copy it so you can npacific old. This is another application. All these things in here. So now I'm going to remove some of the stuff that I don't need. This one, and I'm going to move run into interactive. I'm going to edit this, and as I did for the other one, it's already configured for the npacific, so this is fine like that. Although I'm running .in file is npacific. At this point I'm going to try to see whether the model runs in an interactive way, but we should use a Q-sub system. And the first thing it says partition error, and that's because the number of processors in the in file is different from the one specified in here. In fact, this wants to use 16, but I only specified to use 8 processors. I'm just going to correct that, and I'm just going to stop running. And the model is running. So at this point, you just wait until you're done with your 10 years of run, and then in the next demo, we're going to start looking at the output of the model. So this concludes this demo. Thank you.